Um, I guess I'm back. This is David, and you're watching, I think, the fourth video in this series. We've mentioned, well, we've talked about Sangria and Nova to explain this pre-proof recursion. And now I'm going to talk about the actual IVC and PCD, which were the real way of doing recursion and proof composition before Sangria and Nova came pretty recently. So let me add a new page for that. Okay, so let's talk about the naive proof composition approach because a lot of people are talking about proof composition and IVC and PCD, and it all looks so complicated when people talk about that. But the main idea of it is that when you have a proof, you can verify it with a verifier. If you remember our API, um, actually, oh, I wish I had kept this API. I should not have deleted it. But our verifier, sorry, the arrow should be in this direction. Our verifier takes a proof, takes a verifier key, which is a compiled circuit, and takes a public input, and then returns true or false. Well, so so that verifier thing here, you know, let me do this. That verifier thing here is a program. And when we do zero-knowledge proof on circuits, when we want to prove the execution of a circuit, our circuit can pretty much implement any program. So why not implement a verifier in a circuit? And that's pretty much the kind of like, the trick behind proof composition or recursion or whatever. Like we have a circuit, it's our circuit, and the first part of our circuits is a verifier or a verifier circuit. And it takes a proof and it takes a verifier key, but the verifier key could be, hard-coded in the circuit. And it takes a public input, and we can enforce in the circuit that it returns true, equals true. And that's it. That's basically it. And this circuit can be proven, and so you can obtain a new proof from it. But that's all there is to proof composition, or at least that should show you that the basic ideas are really basic. The zero-knowledge proofs is to prove execution of circuits, and a verifier can be implemented as a circuit. Okay, now if you want to do proof composition that does something additionally, usually you will have your another part in your circuit, like a sub-circuit, I guess, that does some application. We've seen that with Nova. There's nothing different here. Your application will take some inputs and will get you some outputs. And it might even take like some previous state or something like that, let's say. Or let's say outputs of um, of let's call it A. And here we have proof of A and pub of A and VK of A. So that you can imagine there was like something previously that some other circuit A that produced a proof and also produced an output. By the way, public outputs are basically part of the public input, but it doesn't really matter. You can imagine that this was a public output and this was a proof. And to create it, we also used some public inputs. So pub outputs, and this is public input. And that's basically what proof composition is about. And I think I'm gonna stop here because I wanted that video to be very short to sort of introduce this idea and really show that there's nothing more than that when you want to do proof composition.